the 9 posters set up. So if you're one of those 2 posters set up, now would be a great time to go do it. And we'll do our network security session. Hopefully we'll end a little bit early. We can have more time for lunch discussion. And with that, Sara, take it away.
Hi, I'm Sara Wrotniak, and I'm going to be presenting our work about provable security of public key infrastructure, which is joint work with Jaime Leibovich, Evasit, and Amir Herzberg. So why should we study provably secure PKI schemes? Well, applied cryptography is based on certificates, which are authenticated by PKI schemes, the main ones being PKI-X and certificate transparency, CT. And so we need secure PKI for security of applied crypto. And there have been multiple PKI failures, and multiple increasingly complex PKIs are being deployed, which include certificate chains, revocation, and even certificate transparency and other features. And these proposed PKIs are often complex, for example, blockchain-based. So there's a challenge to define models and requirements which are suitable for these complex PKIs. And so what are secure PKIs and what is a certificate? We define a certificate SCI as a signed encoding of a set of name value fields, which include fields like the subject issuer, the validity period, and, for example, a public key, PK. And the PKI scheme includes algorithms for establishing trust in keys or certificates. And this includes certifying them, which is done by an issuer called a certificate authority, revoking by the issuer, and validating, which can be done by relying parties like browsers, using a root store of certificates and other auxiliary information like certificate chains and certificate revocation lists. In addition, certificate transparency also logs, monitors, and audits certificates. So this is done only in CT and not in PKI-X. So one of the contributions of our work is to define some of the key properties, security requirements for PKI schemes. But before I introduce those properties, let's look at an example, which is how certification and validation is done in PKI-X. So in PKI-X, a relying party like a browser might get a certificate size 0 from a website like bob.com, and I need to validate the certificate chain, which comes with the certificate. In this case, it has to check that every next certificate includes a public key that verifies the current certificate, all the way up to a certificate which is in the store, which is like the certificates are trusted, the root store, by the relying party. And not shown in this figure is also certificate revocation lists, which have to be checked to check if certificates have been revoked. So we have defined or identified 4 very important security requirements for PKI schemes, and let me just give you an intuitive overview of these 4 requirements. So the first one is unforgeability, and unforgeability means that if a certificate size 0 is valid and the issuer listed in the certificate is benign, then either it must have really certified size 0, or we can find a fake certificate psi 1 where the subject is the same as the issuer in psi 0, but the public key in psi 1 isn't actually a key belonging to the issuer. The second property is accountability. So if a certificate psi 0 is valid, then we should be able to identify some accountable entity or a bad root certificate. Next, we have revocation. So intuitively, if a certificate is revoked by its issuer, it should not be valid after some delay delta. And lastly, there's transparency. So this is relevant to PKIs like CT, which means that if a certificate is valid, then it should be included in a public log within some delay. So these are just informal definitions, but how do we go from this to formal requirements? Well, we use the MOS framework, which stands for Modular Security Specifications, to define the requirements. So I will use unforgeability to show you as an example. I won't have time to go through all of the requirements, but first need to give some background on MOS. So in MOS, we define requirements using predicates over an execution transcript. And we say that a protocol satisfies a requirement predicate under a model M if for any adversary, BPT adversary that satisfies the model, the predicate holds with overwhelming probability. And this is over random transcripts from the execution of this adversary with the protocol. And so for unforgeability, it would say that P satisfies pi EUF, which is the unforgeability requirement predicate, under model M if for any BPT adversary which satisfies the model, the probability of the predicate being true is close to 1. And we have in MOS the execution process defines how the protocol and the adversary interact. So this is a figure illustrating the execution process, and I won't go into much detail here, but the idea is that the adversary controls much of the execution and can interact with different parties which are running the protocol. And at the end, a transcript of the execution is returned. So this is what this exec is in this definition that we looked at before. So now we know how we define satisfying a requirement in MOS. And we also know where the execution transcript comes from. So all we need to do is define the predicate for our property unforgeability. So how do we do that? Well, this is the informal definition that I mentioned before for unforgeability. So if a certificate is valid and has a benign issuer, then it must have really been certified, or we have to be able to find a fake certificate for this issuer. So we can rephrase that a bit and say that the predicate has to output bottom, meaning the adversary wins, if it can output a certificate psi 0, which is valid, and yet it wasn't certified by the issuer, which is benign, and there is no fake certificate for the issuer. So this is what I just said. And now, how do we translate this into a MOS predicate? So this is a predicate. And you can see the colors correspond to the different parts in our definition of unforgeability. So in line 2, we parse the transcript to get the output of the adversary. In line 3, we check whether the certificate is valid. In line 4, we check whether it was really certified during the execution correctly. In line 5, we check whether the issuer is benign or not. And in line 6, we check whether there is a fake certificate for the issuer. So this is all precisely defined. And of course, in line 4 and 6, the two functions are also defined in pseudocode, though it's not shown here. So in our work, we also analyze specific PKIs, PKIX and CT, and we showed that both of them satisfy the unforgeability requirement under this model, which is the conjunction of a corruptions model and a correct initialization model. And the intuition for the proof is that we do a reduction to the unforgeability of the certificate scheme C. But it didn't say what C is, so let me give you some idea about certificate schemes. So in the work, we define this abstraction, which basically is used for signing of structured information. Like different PKIs can have different encodings of fields. So to make it convenient, we use a certificate scheme, which includes algorithms keygen, certify, verify, and extract. And we also define an unforgeability definition for certificate schemes, and we showed that how to construct a generic provably unforgeable certificate scheme from an unforgeable signature scheme and an invertible value encoding data. And we think this is also useful not only for public key certificates, but also for things like CRLs, STHs, ROAs, and other structures, because a lot of things are certified. So there's a lot that I didn't get to cover in this presentation, including the definition of other requirements, accountability, revocation, and transparency. And we have defined the multiple variants actually of two variants of revocation: guaranteed revocation and accountable revocation, as well as three variants of transparency: guaranteed transparency, audited transparency, and honest logger transparency. And we prove for PKX and CT that they also ensure accountability. We prove that they ensure accountable delta revocation. Actually, we show that they do not achieve guaranteed revocation by showing an attack. And we also show that CT ensures honest logger transparency. And interestingly, it doesn't ensure guaranteed transparency either. And CT with audit ensures audited delta transparency. Where CT with audit is another variant of CT with like an auditing mechanism, which is an option in Google Chrome. And you can see that in these different theorems, we use different models, which is a nice feature of MOS, where we can separate the models from the requirements easily. Future work includes defining other requirements, for example, privacy, as well as analyzing other PKIs and looking at different types of protocols like blockchain-based protocols and broadcast protocols. Thank you.
Hi, thanks for your talk. How and why did you, or one, how is this different than the analysis of PKI in the universal composability model? And then second, why did you choose to, if the reason is that it's because it's modular, why did you choose to use MOS instead of the UC model? Because there have been papers that have done like a UC analysis in a modular way. So I'm just curious on your choices on that.
Well, UC, first of all, the key difference is that this is a game-based framework, whereas UC is simulation-based as well. Even though UC, there have been like ways to try and introduce some modularity, we believe that MOS is really like an intuitive and easy way to break down requirements and models. And it would be interesting to compare different ways that have been done using UC as well.
I don't know if this is related to Julie's question or not, but so I know what a signature scheme is. Like I can write it down. Can you give me some sense of like what a PKI scheme is, like how PKIX differs from CT?
For the first question, a PKI scheme, we define in our work to have certain operations really that have to do with the PKI functions, right? And then we can differentiate, like we can look at different PKIs like PKX and CT, and CT may have some additional operations like for logging and monitoring, right? And then achieve different requirements that we have defined.
Hi. So I'm curious about the last two definitions that were part of the what you were talking about. What has to do with the certificate revocation, the deltas, and so on. What kind of communication model are you envisioning for publishing certificate revocation that these fit into?
So you can see that in our analysis. for revocation, like we assume, actually, we don't assume any kind of like guaranteed communication. And then for transparency, we do assume the communication model, which is a guaranteed bounded delay communication. So it differs between revocation and transparency. But the models are precisely defined using the MOS predicates.
Yeah, I have 2 questions about the MOS framework. So, is it like an attempt to make like game-based notions of security composable? And then, I guess for base level understanding, right, to take the models as like the security experiment in a standard game-based notion of security, and the requirements as like the adversary's winning condition.
So, sorry, I already forgot the first question, but the second question, right, one of the things that MOS provides is to define the models and their requirements separately. And basically, like it's like game-based definitions, but we reuse the execution process, and then we can reuse the different predicates and analysis of different protocols.
And what was your first question, Sam?
Oh yeah, so was the MOS framework meant to try to make game-based frameworks like generically composable?
Oh right, composability. Actually, MOS does not provide composability, but that is one of the things that we are working on. So, right, we want to provide composability and think it can be done using the framework or some extension of it.
All right, we'll do one more question just because we're still early. Although,
Thank you for the talk. My question is about the delta revocation, and I know the slide says beyond presentation, but and so you talked about time-bound communication, but certificate revocation can get complicated depending on which method you're using. If you're using CRLs, OCSP with stapling, and then with certificate transparency, can you talk a little bit about how you analyze the different ways of doing revocation?
So in our analysis, we simply we assumed that CRLs are used, but the requirement can be used with different mechanisms. But for the purpose of our analysis, we assumed CRLs, and so therefore we didn't need to assume like guaranteed communication.
let's thank Sara, and she'll be here for more.
Right, hello everyone. I'm Dee from Brown University, and today I'm going to talk about the BPF-Box, hardening BPF against transient execution attacks. This is a joint work with my lab mate Alexander Gaitis and my advisor Vasilios Kamirlis. So we have been using a model of strong separation between OS kernels and application for several decades. But in this model, context switching and the additional cost of data copying can be at odds with modern computing infrastructure's needs, which tend to be more distributed and more performance demanding. BPF is a feature in Linux kernel that represents a method of bending the line between the kernel and the application, and put more application logic into the kernels to avoid these costs of separation. Think of it like a JavaScript for OS kernels. But it has been shown that even if BPF itself doesn't introduce new vulnerability into the operating system, it can assist and magnify security problems inside the kernel, which is one of which is transient execution attacks. By the way, in this talk, I will be using kernel and operating system interchangeably. So and the BPF-Box we're proposing BPF-Box as a new framework for hardening BPF against such type of attacks. So first, I will be talking about some background and motivation. What is this magical BPF thing, and what is transient execution attacks, and what are the motivation and challenges in addressing the insecurity of their combination. And then we'll go through the BPF-Box's core design, and then I'll show you some evaluations and results of our system. BPF was invented for user application to safely delegate computation into the kernel. And it is defined as a small virtual architecture with RISC-like instruction set. It has a lot of applications in networking and security and in high-performance storage and in other areas too. The instruction set contains things that you expect from a RISC instruction set. It has ALU, it has memory accesses, it has conditional branching. And the safety of a BPF program is guaranteed by a sophisticated static analysis that's carried out by a piece of code in the kernel that is usually called BPF verifier. So the verifier will try to make sure that the program doesn't access memories that it shouldn't be, and also make sure that the program always terminates. You can probably tell that BPF programs are not Turing complete. But regardless, it should be quite flexible and able to encode non-trivial logic in the BPF programs. And generally, when the verifier is not sure about whether a BPF program is safe, it will just reject the program, and such that there's no false negative in identifying safety problems. So at runtime for performance, BPF nowadays supports JIT compilation, such that it runs faster. And when it's running, it has access to the environment containing BPF context, which is the data passed to the BPF programs by the kernel, and BPF stack, which is the scratch space for local variables, and BPF maps, which is a set of persistent data structure that is for BPF data storage and also communicate with user application. So BPF generally works like this. Let's assume that the user wants to have some statistics for incoming network traffic on a machine. So naively, what you would do is you have the operating system. Every time it receives the data, it goes to the application and tell it we received the data. Context switch, with the context switching and the data copying, and then the application will do something, act upon the data. With BPF, what you can do, or the application can encode its hottest computation into a BPF program and put it directly into the kernel. So whenever a data packet comes in, it will go to the BPF program. The BPF program will probably use some of the stack space and some of the map information to do some computation. And then it will aggregate, in this case, the statistics into the BPF map, and sometimes the user and return. So sometimes the user application can come in, do a system call to query the BPF map to see what's happening and with the statistics and aggregated results. But the actual hot path of the data handling happens exclusively in the kernel, and there's no context switches in that case. So that's a super simple version of how BPF works in general. And now we look at transient execution attacks. So due to pipelining and memory being much slower than CPU clock speed, modern CPUs have these optimizations like out-of-order execution and speculative execution. What it means is that they try to execute instructions based on some context that the CPU guessed, which is not available at the time when it's trying to execute it. So when these guesses are wrong, these executions of instructions needs to be reverted in the CPU, and or sometimes it's called squashed. And these squashed instructions are what we call transient instructions. So at some point 5 years ago, people realized that transient instructions or transient executions can have security implications. The way it works is this. So first of all, because transient executions are based on guessed context, it doesn't necessarily follow the semantics intended by the programmer. So things like permission restrictions, sanity check, other invariants of the program can be broken under transient execution. On the other hand, we call it transient execution, but it's not fully transient. So when CPU try to revert state, there are some internal CPU states that cannot be easily inverted. For example, the state in the cache. If you evict certain cache line, you cannot easily just bring it back without defeat the whole purpose. So these 2 points combined, we have it means that the CPU can just leak information even when the program is perfectly correct. So here is one of the oldest example of transient execution attacks. This one specifically belonged to a family called Spectre PhD, also known as Spectre v1. On the right-hand side is a vulnerable snippet of the code. So what will happen here is that X will be controlled by the attacker. Probably, it can be a value that comes in through a web request, HTTP request. So, and X can be larger than the array size. What will happen here is that the CPU, if it wrongly speculates that this branch is going to be taken, it will go into this branch and speculatively dereference a out-of-bound value because X is greater than the size of the array, and this value can potentially be secretive to the application. And then in the next line, the secret value will be used to do a memory dereference, which will encode this secret information into the side channel, which can be recovered later. So BPF can make this thing worse in two directions. First of all, because of BPF's expressiveness, the attacker can now create any code pattern in the kernel without requiring them to exist in the kernel naturally. And second of all, these like vulnerable BPF programs can be executed without thousands of lines of other code in the mix, because BPF tends to sit on the hot data path, and people tend to remove code from the hot data path, and therefore, there's only BPF there. So the BPF feature makes it a perfect accomplice for transient execution attackers. And so there are some existing mitigations in the Linux kernel to deal with this. For example, they try to restrict either BPF's expressiveness, or they try to stop dangerous speculation in BPF. But they have major limitations in terms of compatibility, performance, and the protection scope. So as a result, BPF nowadays are basically privileged feature, and which is limiting, and it limits its potential and usefulness, basically. So now we talk about BPF-Box and how we plan to solve this problem. The key idea here is that speculation is fine. We can allow any speculation as long as we sandbox the whole execution inside a fixed region, such that no sensitive data will be accessed during speculation. The attacker can still make BPF speculate however they want and break all the barriers, access all the wrong pointers, but it will remain in the sandbox, and no sensitive data will be in the sandbox, therefore no exposure and real damage. The way we sandbox the BPF runtime is taking some techniques from what is called software fault isolation. So we will because we will have a sandbox of 4 GB in size, and because it's 4 GB, we can transform the BPF pointers into 32-bit values, and each user will have their own sandbox such that they don't leak information from each other. And we'll put data that are required for BPF to run into the sandbox, which includes BPF stack, BPF map, and BPF context, as we mentioned before. The exact instrumentation kind of look like this. So the top is a hypothetical BPF program. It first loads a pointer into R2, which is a register, and then it does some pointer arithmetics, and it dereferences a pointer in R3. So originally, it's going to JIT compile into the bottom left. The pointer will become a native pointer. And then in the dereference, it will translate into a direct dereference. So you can imagine if R3 or RCX here is speculatively out of bound, executing this will speculatively load a secret value, out of bound value, into register RDX, and further speculation may bring this secret value into the side channel. So instead, under BPF-Box, what we do here is that on the top of at the beginning of the whole BPF program, we will load the base of the sandbox into a register, and it stays there during the entire execution, so no speculation can happen to that. And then we transform the pointer into a 32-bit value, hex 1000 here, and the there's a pointer of arithmetic as usual. Then the dereference will be translated into these two yellow instructions. For those who are not totally familiar with x86-64 assembly, move ECX to ECX will clear the upper 32-bit of RCX, therefore making sure that it's between 0 and 4 gigabytes. Then we will add it to the base address of the sandbox and dereference the correct memory address. So regardless of speculative value of RCX, this memory dereference will always target something, will always target the 4 gigabyte region starting from R12, which is the base of the sandbox. So now we have solved the problem of how to restrict BPF programs' access into the sandbox. Now we just have to put everything that it needs into the sandbox. So first we can deal with BPF stack. It is only used by BPF programs, so it's kind of easy. We just put it into the sandbox. Although there's one interesting thing here, which is we don't want to allocate and deallocate memory all the time when we execute a BPF program. So we have a pre-allocated per CPU region to act as a stack, and there is the stack pointer that maintains the allocation of this region, such that we don't have to call malloc, and not malloc, but something equivalent of malloc in the kernel every time. So for BPF maps, we needed to change the in-kernel data structure to split the data and the metadata, and data can go into the sandbox, and the metadata need to stay out of the sandbox. For BPF context, the complexity here is that the context is a piece of kernel data produced by the kernel, but it's needed by BPF's execution, therefore it needs to be copied in after it's created. Memory management-wise, it's similar to stack. It's created every time BPF is called, so we're reusing the stack pre-allocated stack region. So copying context is sometimes actually expensive. We came up with domain-specific optimization for BPF that leverages BPF's simplicity and analyzability. I won't get into details here, but overall, we find ways to reduce copying to only the essential fields, or sometimes we can just get rid of copying the thing altogether if we can statistically know that they're safe. Now we can show some performance numbers. This is a synthetic micro benchmark that we wrote, which contains BPF programs that stress different kinds of BPF program behaviors. Overall, so the four bars here are no mitigation, current mitigation in Linux, and other two versions of optimized BPF-Box. So our most optimized version of BPF-Box here has around 0 to 23% of overhead compared to no mitigation, where the largest overhead comes when it's hash map heavy on this side of the map. For the current mitigation, generally there's no overhead, but for stack heavy BPF programs, it has over 200% overhead, which leads into the next result. So we did a performance on a program on an application called Catron, which is a load balancer, which is like a bigger piece of BPF program. So in this, our most optimized scheme has an average on average 18% overhead compared to no mitigation, but the existing mitigation, because big programs tend to use stack, will incur on average 112% overhead. Therefore, we are performing quite a bit better than the existing mitigations. So to conclude, BPF is important, but prone to transient execution attack. We mitigate the problems by sandboxing BPF runtime. It makes a BPF-Box more efficient, more secure, and maintain compatibility. This work is currently under submission, so yeah, maybe you'll see it at some point in the future.
Questions?
Thank you, nice talk. One thing, just to make sure I got this right. When you, on the last slide on the performance, the no mitigation is not the thing running in user land, right? It's in the kernel, but no protection against side channel.
Yes. So yes.
Okay. So in user land, how much worse is it? Because the whole motivation was to move back into the kernel to actually get rid of the overhead from context switch and whatnot.
Yes. So the point of let me get so people use BPF to not have computation in the user space, and this particular application, Catran, doesn't have a mode that runs in user space.
Oh, there is not even a new user world.
Yes, there is no like user space alternative to this. There's no.
Gotcha.
No.
And fundamentally, the idea is that you're virtualizing. You're adding a layer of virtualization.
You can see it that way. Yes.
Yeah. Okay. Thanks.
Nice talk. I was wondering what your threat model is. Are you assuming that the attacker has root access to the system?
Yes. So the threat model is that the attacker is a unprivileged user on the system, and it will have access to BPF, which is currently privileged, but we assume that it has because that's the point, and it has the ability to trigger speculation during the execution and arbitrarily direct the speculation and arbitrarily reorder the memory accesses in speculation. So the goal is to let it not gain any advantage exploiting BPF. If it already has some side channel to leak kernel information, whatever, that's the goal.
So the attacker can't install a new BPF. The BPF is there.
The attacker can install new BPF, which is included in the BPF functionality.
And just a silly one, because this isn't my area. How do I make sure that I don't speculate over your like clearing of the top 32 bits? How do I make sure that instruction's not skipped?
So the thing is, speculation do not ignore. So speculation happens for first of all, the general answer is nowadays I don't think there's any form of speculation that can bypass this. And the deeper reason is speculation is needed when something is fast, the CPU is fast and other things are slow, right? Here, the instrumentation here is, the clearing of the 32-bit is very fast, so there's no reason that any CPU would jump over it to speculate past it. So, and currently there is no, to my knowledge, there's no such CPU.
Thank you very much.
Okay.
Cameron has the delicate task of being the last one before lunch, but we're early, so don't rush him. But maybe though.
Did you put the schedule together?
Yes.
Okay. Hi everyone. My name is Cameron Morris. I'll be presenting BGP-iSec, improved security against of internet routing against post-ROV attacks. Internet routing is a large challenge, and it's a challenge that has been around for a while. BGP is, as of this year, 35 years old. And we don't have time to cover all 35 years of history, all of the background, but I know not everyone here is a network security person, so I am going to cover some background and go over this quickly. So the internet is composed of over 80,000 autonomous systems. These are independent or mostly independently managed organizations. Many of them are for profit. These include your ISPs, cloud service providers, content delivery networks. And each of these autonomous systems announces some number of IPv4 and or IPv6 prefixes. These prefixes are address blocks, and there are a lot of them. So to coordinate routing between ASs, each of which are mostly independent organizations that have their own goals, the IETF proposed that we separate inter-AS routing from intra-AS routing. The intra-AS routing being routing protocols like RIP, OSPF that focus on routers, operate on router-by-router hops, and usually optimize for the shortest path, the most efficient path between two destinations. Inter-AS routing is done with BGP. BGP is, instead of operating on the router-by-router hops, it works a level of abstraction higher on the AS paths, so the AS to AS hops instead of routers. Some people call this policy-based routing instead of shortest path routing because it's more about respecting rules with regard to business relationships and choosing the best path that way. So the basic rules that should be respected with BGP: you should only announce your own prefixes. You should only relay announcements that you've received. You shouldn't modify them. By preserve integrity, I mean you shouldn't modify them in any way that would go against the intentions of the original sender. And you should follow what we call valley-free routing, which maximizes profits and customer connectivity. I'll talk a little bit more about that on the next slide. So routing attacks. It has been known for a long time that BGP lacks authentication. BGP sessions are often authenticated between the individual routers at the borders of autonomous systems using IPsec or TLS, some mechanism, but that still leaves BGP vulnerable to rogue AS attacks. These are, for example, one could be a route leak, and in this example, our attacker sends a route leak to AS3. This is a route leak because it's starting at AS11. We see it go up to 1, over to 2, down to 666, and then back up again to 3. This down and back up is a valley. This is what we mean by a violation of valley-free routing because it has a valley. Other attacks, we also have prefix hijacks. In this case, the attacker could announce 1.2/16. This prefix is owned by 11, not 666. We have subprefix hijacks, which are, in this example, they could announce 1.2.3/24, a more specific subprefix of that 1.2/16. We have origin hijacks, where the attacker falsely claims to be a neighbor of the true origin. There's no link here between 11 and the attacker, but the path that was announced has 11 next to 666. We have path manipulations, which is a more general kind of attack. This is any case where the AS path in the announcement doesn't reflect the true sequence of ASs that the update traversed. In this case, we've removed AS1. And then finally, we have attribute manipulations, which are the addition, removal, or modification of other path attributes besides the AS path that can significantly change the meaning of a BGP update. And for example, the black hole attribute would change how that would be interpreted. In this work, we focus on what we call post-ROV attacks. The reason is that RPKI ROV is an existing defense that has been proposed by the IETF, and it mitigates prefix and subprefix hijacks. It has seen widespread and is seeing growing deployment, so we take the optimistic view that at some point in the future, prefix and subprefix hijacks will be a solved problem. But that still leaves us with these other 4 that we look at in this work. We are not the first people to think of post-ROV attacks and defenses for them. The IETF has proposed BGP-iSec as their standard defense against path manipulations. The way that BGP-iSec works in a nutshell is that instead of using the unauthenticated AS path attribute, the routers use secure path segments, which include signature blocks, which authenticate the AS path information, the current AS path information, and also the next hop, the next AS in the sequence. So here AS1 will sign its AS path and that it's sending to AS2. 2 will verify one's signature, sending then its signature onto AS3, and 3 will verify the signatures of 1 and 2. One of the problems with BGP-iSec is that if it encounters an AS that is not adopting BGP-iSec or BGP-iSec, it will not include any of the signature information. So although AS5 here is running BGP-iSec, it can't authenticate any of the signatures added by the prior ASs, which leads to very limited benefits in partial deployment. So why does BGP-iSec do this? There are a few reasons. We discuss more of them in the paper, but one of the main reasons is that BGP-iSec has no registry of adopting ASs. So even if an AS, so an attacker can just drop a signature. It can drop as many signatures as it wants because there's no way to tell if a signature has been removed. And in fact, it's allowed that any AS that has adopted BGP-iSec can stop signing at any time. So we see a few areas to potentially improve on the security of BGP-iSec. First, the security benefits are limited to these BGP-sec islands of contiguous BGP-sec ASs. The two is the downgrade attack is trivial for on-path attackers. They can remove the signatures. Three is that there is no defense against route leaks, which, to be fair, was not an original design goal of BGP-sec. However, it is a post-ROV routing attack, so we wish to defend against it. And four is that something we haven't really talked about too much, but that only the AS path is protected in BGP-sec. So these other attributes are not necessarily authenticated, or they're not authenticated in BGP-sec, which leaves it vulnerable to path manipulation, attribute manipulation attacks. At this point, I also want to acknowledge that there are significant performance issues with BGP-sec that also need to be addressed before adoption. But in this work, we only focus on the security aspects. Which brings me to our contribution, BGP-iSec. This is a set of modifications to BGP-sec where we aim to improve the security of BGP-sec, and especially in partial adoption. Specifically, we want to prevent unauthorized downgrades. So we do have a registry of adopting ASs, and we can prevent those signatures from being removed. We want to enable partial path verification so that the security benefits of BGP-sec can extend beyond those islands. We authenticate integrity-protected attributes to protect against attribute manipulations and also prevent route leaks. We evaluate BGP-iSec using simulations. These are custom extensions of the BGP-I simulator. The link here is to the BGP-I repo. The link to the custom extensions is provided in the paper. We assume a few things for the simulations. One is that we are in a post-ROV scenario. By post-ROV, we mean 100% coverage of prefixes by ROAs and 100% ROV enforcement by all ASs. We don't need 100% in practice. Really, all we need is enough to make it so that those prefix and sub-prefix hijacks are no longer practical attacks that the attacker would consider. But for simplicity in our evaluation, we assume 100%. We also assume valley-free routing with the export to all assumption. We use the CADA serial 2 graph for AS relationships. And we assume there's some mechanism by which the ASs can know the other adopters and their public keys, such as the RPKI. We present our evaluation in terms of the individual components. So we start with the path integrity defense, which is transitive signatures, and then go into 3 separate route leak defenses. Transitive signatures are in BGP-iSec are like BGP-sec signatures, except we set the transitive bit to true and send signatures to non-adopting neighbors. In this example, 1 is doing that to non-adopting AS2, and what that means is that 3 can verify the first 2 hops of this path because 1 signs that it is sending to 2. So 3 doesn't verify the entire path here, but it can verify the first 2 hops and ensure that 1's signature has not been removed. In our simulations, we found that this works, this has a large impact. So here in this data point, as we approach 100% adoption, we're about halfway to solving the problem of post-ROV routing attacks, just by preventing downgrades and authenticating partial paths. There is overhead associated with this in that the non-adopting ASs need to store these signatures in their routing tables, and they need to forward them along. But on the other hand, this orange line here showing BGP-sec shows the cost of not doing that overhead. To solve the other half of that problem, to really get down to 0%, we need a route leak prevention mechanism. The first route leak prevention mechanism is signed only to customer. This uses an existing attribute proposed by the IETF in RFC 9234 that indicates when a route should only be propagated downward to customers. So here in this small topology, AS1 sends it upward with no OTC, but it gets sent downward with an OTC because at that point it should only be further propagated downward to other customers. The OTC attribute, as it is defined in the RFC, is unauthenticated, which means that it only protects against accidental route leaks. This has value still because a lot of route leaks that occur in the wild today are misconfigurations. They are accidental. So we do see some real-world deployment of the OTC attribute, and it is having a real impact. But by not being authenticated, it can't protect against intentional route leaks where it's not authenticated, so the attacker can just remove the attribute. In BGP-iSec, we authenticate the attribute using transitive signatures to protect against route leaks. And if you look at the purple line here, that works, which is exciting because we've taken two existing protocols with some modifications to BGP-iSec and authentication to the OTC attribute, which is in use today, and we eventually get to a 0% attacker success for post-ROV routing attacks, which is nice. But we didn't stop there. We also have two other route leak prevention mechanisms that will fill the rest of the space on the graph and perform better in partial adoption. The first is of the novel route leak prevention mechanisms is, we call them up attributes. The up mechanism works by having two attributes, the up preimage, which is a random string, and an up image, which is the hash of that random string. When both attributes are present, an attribute is, or an announcement is permitted to be propagated upwards. When it is sent downward, only the image is included. So the preimage is not present, and since the hash function cannot be reversed, there's no way to re-add that random string and then propagate the announcement upward. In simulations, this does better than the signed OTC. However, it has the large drawback of an eavesdropping adversary is likely able to capture the pre-image. And to expect that an adversary might be able to eavesdrop is not unrealistic. There are public route collectors, there are looking glass servers, and other mechanisms by which an attacker may be able to get this attribute. So to mitigate that, we developed the provider cone ID mechanism. The provider cone ID works in that an AS1, for example, will build a list of the nearest adopting BGP-iSec ASs. In this case, it adds 2 and 4. We skip 3 because it's not adopting, and we skip 5 because it's beyond the nearest BGP-iSec AS. And that means that ASs 2 and 4 are the only ASs that should accept a BGP update on a customer interface from AS1. In full deployment, this ends up looking like ASPA, if anyone in the audience is familiar with that. And this does even better. And the important part about this green line is that it even works. The green line stays the same when an adversary is given eavesdropping capability. So they can see all announcements in the internet, and including any potential pre-images. There is additional overhead associated with maintaining the provider cone ID list, and AS needs to know its provider cone. But what we found looking at the CADA topology is that the average size of this cone is only around 30. So we believe that that is a reasonable amount of overhead. We further analyze it in the paper, but we don't go over it here in the presentation for the sake of time. On the topic of overhead, so we also look at the average number of signatures verified in BGP-iSec compared to BGP-sec. Our intention is not to show here that BGP-iSec is better, because it isn't. It verifies more signatures in partial deployment because of partial path verification. But as adoption approaches 100%, the numbers converge to the same number of signatures verified. In the paper, we also do a security analysis. So we analytically show that under the assumptions of our evaluation, even with some stronger attacker models, that BGP-iSec has no false positives. It prevents route leaks in full deployment and prevents visible route leaks in partial deployment, and provides announcement integrity under full deployment. So in conclusion, we present BGP-iSec, a set of modifications to BGP-sec. We don't mean to intend this as a complete proposal, something that you take to the IETF and try to get an RFC, but we really want these, or hope that these individual mechanisms are useful as a basis to build upon for further discussions of ways to protect, and the right ways to protect against post-ROV routing attacks. So So thank you all, and I'll take questions.
Don't do that. Just because it's the last one. Yes.
When you say percentage of attacks successful, like what distribution of attacks are you measuring over? Like what? Yeah.
That's a great question. So we run randomized, so we randomly select an attacker, randomly select an origin, and then do data plane traceback from all other ASs. So in this graph here, we run repeated trials like a Monte Carlo of pick an origin, pick an attacker, and these are the averages with the error bars here.
So I have two questions, and I'll ask them one at a time. First, looks like really cool stuff. Let me just ask that for this BGP style attack, what is the overall, like at a much higher level, what is the impact of the existence of such attacks? Are they, first of all, are they commonly used, and what kind of impacts do people typically see from this kind of thing? Is it just sort of like denial of service that screws up the internet, or is it something worse?
Yeah, that's a great question. And so the impacts that we see today, I'll go all the way back to the beginning. So the impacts are really to these prefix and subprefix hijacks that I've crossed out here. Because right now those are the most impactful attacks. So if you're an attacker, you want to cause disruption and mayhem, you would do one of those. As far as the impact, so there is the denial of service, like you said, but there's also other interesting attacks. So one example recently, there was a cryptocurrency heist. What they did was hijacked a prefix, I think it was owned by Amazon, and then used that to request an SSL cert or TLS cert, and then used that certificate to host a fake website that got them, and they had a valid cert, so then they were able to steal some cryptocurrency. I think they stole around $200,000 worth. There's some interesting attacks just beyond the denial of service. Namely, you can get a valid TLS cert by hijacking an IP prefix. Is, I think, one of the more interesting ones.
That's very interesting. Also, just to, I think you were trying to get at this, but you maybe didn't summarize at this point. The additional mechanisms you're talking about, they're quite inexpensive, right?
RPKI, ROV generally, it depends, of course, who you ask. But yes, they're for sure less expensive than something like BGP-iSec or BGP-iSec. Yeah.
Okay. Well, I hope you start leveraging this towards like some actual adoption. It'd be better to have better protections.
Yeah, thank you.
Okay, great. Thank you, Cameron. Let's thank all the speakers in the morning so far.